Hi, welcome to Precalculus. Today's topic is Introduction to Complex Numbers. We are doing this to have a little bit of a review for the section on complex numbers in polar form. So, how do we study numbers? Well, we start in elementary school, and then we have first encounter with whole numbers 1, 2, 3, and so on. Then perhaps at some moment we learn about the number 0 and then the negative numbers, and we go on. Next we learn about fractions, perhaps 3/2 and say 7/3, etc. Maybe the negative of these numbers as well. By the time we come to middle school, we have square root numbers, radical 2, radical 3. In geometry, we learn about pi. By the time we come to precalculus, we also have a number e, and we map all of these to the so-called real number line. So we have 0, 1, 2, 3, and these numbers fill this line. So we have the so-called real numbers. Real numbers, sometimes shown by this funny R. At some point, perhaps in high school, we come across certain kind of equations, quadratic equation. First, they are easy to solve, so it's x squared equal to 25. No problem in solving that. We have x equal to plus or minus square root of 25, or just plus or minus 5. Then some of the quadratic equation give us a little bit of a pause. How about x squared equal to minus 25? The answer, we like to write it as plus or minus square root of minus 25, but we pause at what is that? It's neither 5 nor minus 5 nor any other real number that we know, because any real number multiplied by itself is going to be a positive or at the minimum 0. So what is that? The issue is brought to the following level. Well, what if you had x squared x squared equal to minus 1? Well, we write the answer as plus or minus square root of minus 1. And this will be just 5 times bigger than that. When people came across these numbers, somebody, I guess it was Descartes, gave it a name, a strange name. He said square root of minus 1, he's going to call it an imaginary number. Imaginary number. Even though some other scientists suggested other names, this stuck, and so square root of a negative number is referred to as an imaginary number. Now, we have a notation for this that makes life a lot easier and less error prone. We call this thing I. In mathematics, we call that I. In many areas of engineering, they use the letter J for the same thing, because I is reserved for the intensity of electrical current, which you measure with amp. Like when you have a fuse that burned or something, go check it out if it's 15 amps or 20 amps. Various electrical equipment to buy, they have a amperage assigned to it. Okay, in physics you see that they use the letter I to refer to how much electric current goes through a wire, and to avoid confusion, in engineering they use the letter J. But at any rate, if you have square root of a negative number, like square root of minus 4, we can write it as square root of minus 1 times 4. and that is square root of minus 1 times square root of 4. And I can write it as 2 square root of minus 1, and we can write it as 2j or 2i, excuse me, let me just write I, and when you get to your engineering class, just practice calling it maybe j. Sometimes this might not come from under the radical, but that is I radical 3, or if you wish radical 3i, either way. So we have these numbers, and it is important for us to have the following in our mind. So I is a number that when you square it, you get minus 1. That is I times I is minus 1. Another way to write this thing is I is equal to minus 1 times minus 1 divided by I is I. Or minus I is 1 over I. All of these things say the same fact. So we have I is equal to square root of minus 1, and these are some of the basic properties of it. Now let's be careful about some items from middle school algebra we are used to. In middle school, square root of a times square root of b was equal to square root of ab. Is that still true? Well, let's practice in our new situation. Suppose I have a square root of, say, minus 4 times square root of minus 9. We learned the first one is 2i, and the second one is 3i. So it becomes 6i squared, and that is minus 6, because I squared is minus 1. So square root of minus 4 times the square root of minus 9 is not the product of these two. Why? It's not that, because this is 36 and that will be 6. But we showed that it becomes minus 6. So what's the resolution then? How should we be careful here? Let's do another practice. If I have square root of minus 2 times 3, I still have this as a square root of minus 6. If you write it with I, you notice that it is still true. Same fashion, this is also true. The only thing that is a surprise is that if both of these were square root of negative number, a minus appears. So how do we clarify that? Say square root of a times square root of b is equal to, we can still write square root of ab if either a or b or both are positive, either a or b is positive. However, if both of them are negative, then this becomes minus. Okay, just like the example that we gave here, if both of these two numbers are negative, and negative survives. That is, if you want to write it with minus 4 times minus 9, if you want to put them in the radical, that will give you the 6 that you want, but then you want an additional minus in front of it. So it's going to be minus square root of AB if A is less than 0 and B is also less than 0. So that is something to remember. Or if you don't want to remember it, always be careful that if you have square root of, say, minus k, and k is a number that larger than equal to 0, write it as a square root of k times I, and that will help you to avoid kind of sign mistakes that are common in dealing with these type of square roots. Another issue that comes up with respect to the division of two square roots. Again, from high school you remember that if you have square root of 4 over 9, well, you can write this thing with a single radical. Either way you get 2/3. So you can take the square root first and then divide, or you can divide first and then take a square root, and there is no problem either way. The problem we have to investigate is, what if one or both of these, numerator and denominator, is negative? Well, let's try one by one. Suppose I had square root of -4 over square root of 9. So what's that going to be? So this is 2i over 3. And that would be same as having 4/9 negative in the square root and taking 4/9 outside, and square root of -1 is I. So from this observation I get that if I have a square root of a over square root of b, I can go ahead and write it as square root of a over b if a is negative and b is positive. I am safe in doing that. Of course, what we have from middle school is that if both of them are positive, that is never an issue there. So if a was positive and b was positive, well, that's what we are used to, and no issues there. What if both of them were negative? -4 over square root of -9. So that is 2i over 3i. i's cancel, and I get 2/3. And if I take -4 over -9 and divide them, the minuses cancel, and I get 2/3 again. So no problem there either. If I have square root of a over square root of b, that again is the square root of a over b, if it is the case that a is negative and b is also negative. What is left? Suppose I have square root of 4 over square root of -9. What is that? Well, this one is 2. This one is 3i. 2/3, well, that's our regular 2/3. What is 1 over I? 1 over I, we mentioned 1 over I is minus I. So minus I pops in. So this is minus I times 2/3. That is not same as square root of 4 over -9, because this is -4/9 minus 4/9. If you take square root of it, you get 2i3, not negative 2i3. So this is where we have our exception. If I have square root of a over square root of b, and if I know a is positive, however b is negative, this is negative of square root of a over b. And that is our surprise here. So we can paraphrase this the following way. If I have square root of a over square root of b, and I want to write it as a single radical, what we learned in elementary school, a over b is correct if either a is negative or b is positive. However, it's minus square root of a over b if a is positive and b is negative. A bit confusing perhaps, but to avoid this type of issues, it's always advisable to do the following. If you have a square root of a negative number, write it as the square root of a positive number times I, and then do the algebra as usual. then you don't need to memorize this particular rules we just mentioned. This one and this one might look counterintuitive, but if you follow the advice of doing this style, one of the advantages of using the letter I for square root of -1 is that we avoid kind of mistakes with doing our arithmetic. Okay, what is next? Next item up is looking at powers of complex numbers, and let's start with the simplest of these, which is the powers of I. As usual, I to power 0, like any number, power of 0 is just 1, and I to power of 1 is a shorthand for just I itself, and I to power of 2, well, that is the defining property of this whole thing. I to power of 2 is -1, so that is our main property here. How about I cubed? Well, I cubed, I can write it as I squared times I. I squared is -1. How about I to power of 4? Well, I can write it I squared times I squared. Each of them is a -1, and when I multiply them, I get +1. You notice that we are back here. How about I to power of 5? Well, I can write it as I to power of 4 times I to power of 1. I to power of 4 itself is 1, and I to power of 1 is just I. And now we have the following, that this is just I. Same way for other powers. I to power of 6 is I to power of 5 to I to power of 2, and excuse me, to power of let me correct myself. I to power of 4 to I to power of 2. I to power of 4 is 1, and I squared is -1, so I go back to -1, so this is same as this, and so on. I to power of 7 is I to power of 4 times I cubed. I cubed already is -I, and I to power of 4 is 1, so this becomes -I. What we learn is that we are going in a circle. After every 4 we are repeating ourselves. So let's make a wheel like this. Like I to power of 0 is 1, I to power of 1 is just I to power of 2 is -1, I to power of 3 is -I. This is same as I to power of 4, this is same as I to power of 5, same as I to power of 6, the same as I to power of 7, same as I to power of 8, same as I to power of 9, same as I to power of 10, I to power of 11, and so on. Now, if I came across a big exponent like I to power of 203, what would that be? Would I just go around, count all the way to 203? Well, now there's a smarter way of doing this thing. We could write it I to power of 200 times I to power of 3, and then this one is I to power of 4 to power of 50 times I to power of 3. I to power of 4 is 1 to power of 50, that's still 1 times I cubed. So this is same as I cubed, which is -I. So in short, if I have I to some power n, I can reduce it to I to some power r, where r is a remainder of division of n divided by 4. So r is a remainder in division of n by 4. and that takes care of all the simple power questions. Same thing applies with the negative exponent. The same way you can do that. Next up, we are going to look at so-called complex numbers versus imaginary, pure imaginary numbers. So pure imaginary when a number is multiplying just with I, we refer to that as pure imaginary. A real number, of course, like 3, 5, and so on. Complex numbers, sometimes referred to as mixed number, it has both of these things. For example, 3 plus 2i is called a complex number, as a real portion and as an imaginary portion, each of them taking their own spots. And here we have a terminology. We refer to real part and the imaginary part. Imaginary part. So real part is 3, imaginary part is 2. If either of these were negative, we would just reflect that. So if I have minus 7 minus 11i, then I'll say real part, sometimes abbreviated to RE, it's minus 7. Imaginary part, sometimes abbreviated to IM, is minus 11, and so on. Now, to designate complex numbers, they use letters like Z, T, W from the very end of the letters of alphabet. So let's write some of these. So I say Z, and then maybe I'll have also a W, say 5 plus 7i. When I have a bunch of complex numbers, as usual, I want to learn about arithmetic with complex numbers. What does that mean? Arithmetic, of course, it means addition, subtraction, multiplication, division, and power. And by the time you come to calculus, there is also functions to be applied to complex numbers. Well, let's start with the easiest. What about addition of complex numbers? It's very simple. We add the real part, add the imaginary part, so 8 plus 9i. So that was easy. How about subtraction? Is just as straightforward. Take the real parts and subtract them. 3 minus 5 is minus 2. 2 minus 7 is minus 5. So no issues there. What about so-called linear combinations, such as 2z plus 3w? So that's twice 3 plus 2i plus 3 times 5 plus 7i. We carry out these things just like you do in middle school. 2 times 3 is 6, 3 times 5 is 15, add them up is 21. 2i is 2i, and 3 times 7i, so 4 and 21, so that's 25i. This kind of creatures called linear combination. You're going to see a lot of that in the years to come in all of your classes, especially linear algebra, differential equation, and so on. The idea of linear combination simply means you have two entities, you multiply them by some numbers and add them up. Next up is, how about multiplication? That's where things start to become interesting. Z times W. So that's 3 plus 2i times 5 plus 7i. The way we do this thing, first, just like middle school, we FOIL them. The only thing that's going to be different from middle school is that we have to make the observation that I squared is minus 1 and simplify accordingly. So let me write it out first time. 3 times 5, 3 times 7i, 2i times 5, and 2i times 7i. no problem here. 15, no problem here, no problem here. Well, there's been a problem here. 14 I squared, which is minus 14. That's the only thing that's different. 15 and minus 14 is 1. And the other two adds up to 31i. So multiplying them, it's after you get used to I squared being a negative 1, is straightforward. What is interesting and not so trivial is how would you go back? We're not going to talk about that, but perhaps those of you who are interested. Factoring complex numbers is not a trivial thing. It takes a lot more effort than factorization we are used to. Let's just write some general rule here. A plus bi times c plus di, assuming a, b, c, d are real numbers. So it's going to be a times c, real times real, imaginary times imaginary. I squared becomes minus 1. So this is going to be minus bd. And then I'll have AD and BC, each of them multiplying by R. So this is an important formula in complex numbers. Next, we have the so-called issue of special multiplication with respect to so-called conjugates. In mathematics, if you have two expressions, one of them is addition of two items and the other one is difference of the same two items, they are called conjugates of each other. So if I have z, forgetting what was it, 2 plus 3, 3 plus 2i. So 3 plus 2i. If I want to subtract these two things, I have a special notation for that. It's called z with a bar on top of that, and that is read as either z bar, so z bar if you want to, or conjugate, z conjugate. What is special about this thing? Well, you remember again from middle school, if you have product times of the sum and difference, you get difference of the squares of these two. So what do we get if I have z and z bar multiplied with each other? So according to that, I have to get first one squared minus second one squared, or just multiply them out. So 3 times 3 is 3 squared. 2i times minus 2i is minus 2i squared. 3 times minus 2i and 2i times 3, they have opposite signs and they cancel each other out. The same way ab minus ba here cancel each other out. So 3 squared, well, that is 3 squared. This is minus 2 squared times I squared. I squared is minus 1. So let's emphasize again. If I have 3 plus 2i times 3 minus 2i, I get the first item squared and second number squared, added up. Let's practice thing one more time. Say 7 minus 3i. And the conjugate of that is 7 plus 3i. If you have minus, the conjugate is plus. If you start with the plus, the conjugate is with minus. Either way, this is 7 squared and plus 3 squared. So in general, if I have a plus bi times a minus bi, the product is a squared plus b squared. So this is a special factorization for sum of two squares. If you have sum of two squares and you want to enforce factorization, your factors will be complex. Okay, here is as good of a place as any to introduce modulus of a complex number. If I have a number like 3 plus 2i, this reminds us of that hypotenuse of a Pythagorean, of a right triangle by Pythagorean theorem. 3 plus 2i, we are going to introduce this thing later on, is pictured like this, going 3 in one direction and going 2 in the perpendicular direction. So if you go in this direction, you're going in direction of I, and this is in direction of just 1. Well, what's the distance from beginning to the end? Well, that's hypotenuse. We show it like that: absolute value of z, or modulus of z, is square root of 3 squared plus 2 squared. Okay, so that's a definition of absolute value, or the modulus of a complex number. So if I take the modulus complex number and square it, well, I get 3 squared plus 2 squared, which is what I would have gotten if I had taken z and multiplied it with z bar. So let's write this again. If I have z is equal to a plus bi, then a modulus of that is square root of sum of squares, and then we have the following, that z times z bar is same as absolute value of z squared. So let's put that in a box as well as an important item to remember. Next item up is the issue of division. Division of complex numbers. Let me demonstrate this thing by an example. Suppose I have 2 plus 3i over 5 plus, say, 4i. I want to write this thing as a complex number. That is a real number plus another real number times I. How do I do that? Very simple step, which is multiply this thing by complex conjugate of the denominator. That is, I take the fraction that I have, multiply by conjugate of the denominator. So this fraction is of course 1. What's the advantages of this multiplication? The advantage is that the denominator becomes a real number. We just learned that the product of these two is 5 squared plus 4 squared. How about the numerator? I have 2 times 5, that is 10. 3 times minus 4, that is minus 12. I squared is minus 1, so that becomes plus 12. 2 times minus 4i. 3 times 5i. So I cleaned up. This becomes 22. And then plus 7i divided by denominator 25 and 16 is 41. If I want to see the pieces, the real piece is 22 over 41. Imaginary part is 7 over 41 times I. So this is the complex number that's equal to this complex number. So the division is done by multiplying with the complex conjugate of the denominator. How about power of a complex number? Well, that's just repeated multiplication. So if I have like 2 plus 3i and I want to square it, well, what does squaring mean? We just do that. 2 plus 3i times another 2 plus 3i. So 2 times 2 is a 4. 3i times 3i is minus 9. 2 times 3i and 3i times 2i, so let me write them separately. 6i and another 6i. So that's minus 5 plus 12i. So if I wanted to cube it or whatever, I just sit there and patiently do that, or apply the binomial theorem if I remember it. Okay. What if I wanted the root of a complex number? Well, things are going to become a little bit more complicated than what we have right now. That's going to be one of the topics that we are going to cover coming up, but we are going to postpone that, and we'll see that later on. How about plotting a complex number? Suppose I want to plot 2 plus 3i. As we just mentioned, we borrow our Cartesian plane. The horizontal is going to be referred to as the real axis. This is where the real numbers go, and vertical is going to be imaginary axis. So when we say 2 plus 3i, it means go 2 steps to the right, and then 3 steps up, well, perhaps taking better steps than what I drew. So this is same as the location 2, 3 we are used to from the Cartesian plane. We're just labeling it in a new way. So if you had previously we had point that we will write 2 comma 3 in parentheses. Now we are writing the same thing in a slightly different way. We call it 2 plus 3i. Of course, if the real part was negative, I'll go to the left. If imaginary part was negative, I'll go down. And that is the same as what we have with ordinary Cartesian plane. So we started from ordinary numbers, worked our way to complex numbers by starting with the square root of -1. We said the advantage of using the letter I for square root of -1 is to avoid certain mistakes. We brought up 2 surprises from the rules from middle school. Product or ratio of 2 square roots. We have to be careful what we do to avoid any confusion. We said writing it in this style will take care of all the fine points for us. Powers of I, we mentioned that we are essentially going on a circle, and we gave a shortcut for large powers. Then we called the real and imaginary part of a complex number, and we started our way on arithmetic, addition, subtraction, multiplication, division, and power. And then we talked about the complex conjugate, talked about the modulus, important identity here for product of a number and its conjugate. We made the use of that in division of complex numbers. We talked about powers of complex numbers. We postponed the issue of the root to later on. And we said the plotting is very trivial. It's just what we have been doing since middle school. Okay, next up we are going to take a look at polar version of complex numbers. Okay, until then, good luck and God bless.